Welcome back. We're looking at problem number 11 in our review packet. We're looking at solutions, colloids, and suspensions. A quick definition for a solution is that a solution is a homogeneous mixture, meaning that it is uniform in composition. It has the same properties throughout the entire thing. Two examples of this, there's many examples, but salt water, which is solid sodium chloride dissolved into liquid water, so it's a solid liquid mixture, which we just call a liquid mixture. And air is another example of a solution because air is a mixture of gases. So this is a gaseous mixture. Oxygen and carbon dioxide and water vapor and some other trace gases are dissolved in nitrogen, which acts as the solvent because it's the majority of air, about 80%, a little bit less. All right, a colloid is always the fun and confusing one. It is a heterogeneous mixture. If you zoom in and look on it at a microscopic level, however, to the naked eye, it tends to appear pretty homogeneous. Okay, milk is an example of a colloid. It looks like one uniform wet liquid, but if you shine a laser light through it, you can see the path that the beam takes in the Tyndall effect. So we know that it's actually heterogeneous on a particle level, because the particles are big enough to reflect or scatter that light back to our eyes. Another example is fog, which is liquid water droplets suspended in gaseous air. The droplets of water are big enough to scatter light back to our eyes. Again, the Tyndall effect, you can see the beam of light as it passes through. This is why you don't use high beams in the fog, because the extra light, the extra intensity, is just going to scatter it more wildly back at you, making it harder to see. All right? So again, these appear to the eye to be homogeneous, but they are heterogeneous because we can actually see them scattering light. These do not settle out. Okay, not over a short period of time anyway. We're talking hours or even perhaps days. These will not settle out. They might settle if you give them weeks or years, but that's too slow to qualify it as our third candidate, a suspension, which is a heterogeneous mixture in which one component settles out. So the solute settles out of solution. And we're talking pretty quickly because, like I said, milk will settle out if you give it enough time to separate. If you give it a couple of weeks, you will notice a layer of things dissolved in fat, which makes a fairly chunky substance in the milk container, and you will notice a yellowish water layer, which is an aqueous phase, and everything that is in the milk that dissolves in water stays in that particular phase. So yes, it will separate out, but it takes a couple of weeks. A suspension is something that will settle out over a matter of minutes usually. An example would be creek water. If you take a sample of water from a creek that's flowing fairly rapidly, you'll notice it is carrying suspended particles in it. And if you remove all that velocity from the water and you just have a sample of the water standing still, everything that was being carried by that water in suspension settles out, falls to the bottom because it can no longer be suspended by that water. Another example of a suspension is Italian salad dressing. That's the dressing that has lots and lots of heavy particulates inside of it. So if you let it settle, you're going to see that there's an aqueous phase at the top, and then all the dense, flavorful stuff, I suppose, is at the bottom. So to get a good salad dressing spread for Italian dressing, you have to shake the whole bottle up to resuspend everything, the particulates that are in that particular mixture. All right, let's do number 12 on the same video. These are straightforward conversions. 150 kilometers to meters, well, kilo equals 1,000. So 1 kilometer equals 1,000 meters. We can do a little bit of dimensional analysis, or factor label if you prefer. Lots and lots of different names, but what it boils down to, we take our given 150 kilometers and make it the top left of one of our little tic-tac-toe grids here. And then, before I put numbers, I'm going to put units to cancel out. Kilometers down here, and I can go from kilometers directly to meters because that is a known conversion factor. Alright, we know 1 kilometer has 1,000 meters. I've arranged it so that the kilometers will cancel out, leaving us with units of meters in our answer, which is what we want. It's a good way to self-check our problem. So now we're left with 150 times 1,000, so I'm just going to add 3 zeros to 150, and it's 150,000 meters. All right, letter B, 45 centiliters to milliliters. You could make one direct conversion, but I'm going to show you the full two-step conversion here. Centi means 1/100th, and milli means 1/1000th. So 0.01 and 0.001, respectively. So if I set up my conversion grid, I have 45 centiliters. I'm going to convert to the base unit of liters. So 1 liter has 100 centiliters inside of it. Notice I'm setting it up to cancel out centiliters and leave me in liters. But I'm not going to stop there, so I'm going to extend my little grid, and I'm going to do one other step. I need to cancel out liters now and go into milliliters. There are 1,000 milliliters in 1 liter. Notice I'm flipping this conversion because it's 1/1000th, so 1 milliliter is 1/1000th of a liter. Therefore, 1 liter is 1,000 milliliters. I'm just flipping the fraction. All right, so now I'm left with 45 times 1,000 divided by 100. I could just recognize that these zeros are going to cancel out these two zeros and just multiply by 10, and we'll get 450 milliliters. All right, whoops, slid off the screen here. Letter C, 0.0530 grams to milligrams. Well, milli, 1,000 milligrams in 1 gram, because milli is 1/1000th. So I'm going to set up grams down here, milligrams up here. There's 1,000 milligrams in 1 gram. Again, this is because a milligram is 1/1000th of a gram. And I flipped the conversion factor. Now, this is just a one-step problem. I am going to move it 3 zeros over, so 3 decimal places, 1, 2, 3, and I'm going to get 53.0 milligrams. A more convenient number than saying 0.0530. All right, 60 milliliters to cubic centimeters. This one is actually not going to change the number, only the unit, because a milliliter is defined as 1 cubic centimeter. Or if you're going to the medical profession, you're going to see that cubic centimeter written as cc. All right, so 60 milliliters with 4 significant figures given to us is going to convert into cubic centimeters. I'm just going to write it as cc. It's just more convenient. So we write milliliter and cubic centimeters. It's 1 to 1, so 1, 1. 60 times 1 divided by 1 is 60, but we keep our significant figures here. And cc is our unit. Just a quick note on sig figs, if you're wondering why with only 1 sig fig in this, would I keep all 4 of these significant figures? The answer is there's not just 1 sig fig in the number 1, because this is a defined conversion. It has infinite sig figs. So my smallest is the other unit, which has 4. All right, last one, 15 kilograms to milligrams. Well, this is another two-step problem. Kilo has 1,000 grams, so kilograms, 1,000 grams. And milligrams, a thousandth of a gram, 1 gram equals 1,000 milligrams. I set up my two-step conversion chart, so it's going to look like letter B. 15 kilos. Okay, we set up a fraction chart here. Kilogram to gram. There's 1,000 grams in 1 kilogram. Set up one more grid because we want to go to milli, not grams. Grams set up to cancel out. 2 milligrams. There's 1,000 milligrams in just 1 gram. So now we're multiplying 15 by 1,000 by 1,000. So 15 times a million. And we're going to get 15 million milligrams. All right, tune in for the next video to go through the next set of problems.